Hello my dear students, welcome back to your channel. Hope you all are doing well. Today with this video, I will try to cover all important points and formulas of chapter 10, that is wave optics. In this chapter, different topics to be covered are: first, what do you mean by wavefront, then Huygens principle. Using Huygens principle, you have to prove laws of reflection and refraction. This topic is very important. After that, interference Young's double slit experiment and fringe bit, Young's double slit experiment, YDSC. This topic is also very important. Then what do you mean by coherent source, sustained interference and diffraction due to a single slit? This one is also very important, width of central maxima. So I will discuss each topic one by one. Let us start first with this chapter name, that is wave optics. What does it mean? You know, light has dual nature. Sometimes it behaves like a particle and sometimes it behaves like a wave. Particle nature of light already discussed in chapter ray optics. And in this chapter, we will discuss about wave nature of light. We assume that light travels from one medium to another medium in the form of transverse wave. Right? Transverse wave. And its speed depends on the type of medium in which light is traveling. So to discuss wave nature of light, you must know about wavefront, because light travels in the form of one wavefront to another wavefront, from one medium to another medium. So first topic is, what do you mean by wavefront? Okay, you know, suppose there is a source of light, right? And this source of light sends disturbance in all possible directions. Right now, so suppose after time t, in one medium velocity of light, suppose v. So after time t, it travels a distance v into t. Suppose this distance is v into t, this distance is v into t. All these distances are same after time t. Now if you draw the locus of these particles, all these particles which are traveling in same distance are vibrating in the same phase. So locus of all these particles which are vibrating in the same phase are called wavefront. And depending upon the shape of the source of light, this is source of light, depending upon the shape of the source of light, this wavefront is of three types. One is spherical wavefront, cylindrical wavefront and plane wavefront. When a spherical wavefront is formed, here in this case, when the source of light is a point source. When source is point source, in that case a spherical wavefront is formed. If the source is a linear source, this one is point source, a spherical wavefront. Second one, if the source is a linear source, this is the linear source. Again, each point on this sends disturbance in both directions, all directions. So if you join the locus of all these particles which are vibrating in the same phase, you get one cylinder. So this is called cylindrical wavefront. So if the source is linear source such as slit, we get cylindrical wavefront. Then plane wavefront. Suppose the source is at infinity. When the source is coming from infinite distance, in that case this type of wavefront is formed. Plane wavefront. So hope it's clear to all of you. Depending upon the shape of the source of light, there are three types of wavefront: spherical, cylindrical and plane wavefront. Now okay, again there are two other types of spherical wavefront. This one is diverging spherical wavefront, this one is converging spherical wavefront. Suppose the rays are diverging from this point, and when rays diverge, when we use which type of lens? Yes, concave lens. In case of concave lens, rays are diverging. So if you draw wavefront, in that case you get, these are diverging spherical wavefront. If the rays converge at one point, in which case rays converge at one point? Yes, convex lens. Right? In this case we use convex lens. So the rays converge at one point. In this case these are converging spherical wavefront is formed. Right? Now what do you mean by this ray? This is the arrow drawn perpendicular to the wavefront. In this case also, suppose if you draw normal to this wavefront, that normal to this wavefront is called what? Suppose this is normal to this wavefront. So these are rays. Right now, rays are always arrows perpendicular to the wavefront in the direction of propagation of wave. Wave travels from one wavefront to another wavefront right now. So these rays are always perpendicular to the wavefront. If it is a spherical wavefront and these from the center, these are rays. These arrows shows rays which are perpendicular to the wavefront, and this rays shows direction of propagation of wave. Hope it's clear to all of you. Now, next important topic I am going to discuss is Huygens principle. What is this Huygens principle? It is very, very, very important, right? Actually, it is geometrical construction that can be used to calculate new wavefront after some time from its current position, because you know wave travels in the form of wavefront from one medium to one point to another point. So how you draw next wavefront? Okay, for that one Huygens principle is used. It is geometrical construction which is used to calculate new position of a wavefront after some time from its current position. So it is based on two following important assumptions. First one is each point on the given wavefront. Suppose there is a spherical wavefront which is given. This is given wavefront, right? Given wavefront, or you can say primary wavefront. Okay, primary wavefront. Now, each point on this given wavefront acts as a source of new disturbance, and that new disturbance is called secondary wavelet, which travels in all directions with the velocity of light. How each point, this acts as a source of new disturbance, and disturbance travel in all directions. So this sphere is secondary wavelet, right? And if you draw a common tangent over this secondary wavelet in the forward direction at any instant gives new position of wavefront. This one is secondary or new position of wavefront. So there are two important points. Using these 2 points you have to draw next wavefront. Here diagram is clear to all of you. Suppose this is a point source, so this one is the primary wavefront, right? Now each point on this primary wavefront acts as a source of secondary new disturbance, that is called secondary wavelet. These small spheres are called secondary wavelet. And if you draw a common tangent in the forward direction, in backward direction also you can draw, but I am taking here in the forward direction, gives the position of new wavefront, or you can say secondary wavefront. This one is secondary wavefront, right? Why I am taking only wavefront in the forward direction, not in the backward direction? You know, amplitude is directly proportional to 1 plus cos theta. In the backward direction, theta is what? 180 degree. So this becomes cos 180 is minus 1, 1 minus 1 0. So amplitude is 0. It means intensity is 0. Intensity in the backward direction of light is 0, which is not possible. So we always take wavefront in the envelope of that wavefront in the forward direction only, right? This one is a cylindrical wavefront, right? This is linear source. This one is, each point acts as a source of secondary wavelet. So in this way we draw cylindrical wavefront if the source is linear. Now using this Huygens principle, two important questions are there. You have to prove laws of reflection of plane waves using Huygens principle. Very, very, very important. And second, refraction of plane waves. So you know there are two laws of reflection. One is what? In terms of incident ray, reflected ray and normal all lie in the same plane at the point of incidence, and angle of incidence equal to angle of reflection. So you have to prove these laws in terms of wavefront, incident wavefront and reflected wavefront, right? Okay, you know light is coming from infinity, and when the source is at infinity, what type of wavefront is formed? Yes, is plane wavefront. Suppose light ray is coming in this way, and these are rays, incident ray, and normal to this incident ray is a plane wavefront. This one is plane wavefront. You can say this is incident wavefront. Now you have to draw a reflected wavefront and prove that I equal to R. Okay, so you know this one is incident wavefront is means it is AB is incident wavefront, it is a primary wavefront. Now according to Huygens principle, each point on this primary wavefront AB act as a source of new disturbance, it means secondary wavelet. So when the disturbance from this A point reaches to this C, then disturbance from B point at that time reaches to this D point. Right now? So suppose after time t, it moves with velocity v. This disturbance from A reaches to C, disturbance from B reaches to D. It means AC is equal to BD. Right? This one is also V into T and this one is also V into T. Now, what is the second step of this Huygens principle? You draw one envelope or common tangent over this secondary wavelet. This is secondary reflected wavefront or new wavefront, right? And normal to this reflected wavefront is reflected ray. Ray is always normal to the wavefront. So now this is incident wavefront AB and this CD is reflected wavefront. This normal and incident ray, it is angle of incidence I. Now this ray and wavefront, they are perpendicular 90 degree. It means this angle is how much? 90 minus I. Again this is 90 degree. So this angle is I. So angle between this incident wavefront and this reflecting surface XY is what? I. In the same way, this is normal. This one is reflected ray. So this is R. And again, by applying this, you get angle between this reflected wavefront and this separating surface is R. Now you have to prove this I equal to R. How you prove? You consider these two triangles. Triangle incident wavefront is ABC. Triangle ABC and reflected wavefront CD is there, na? So BDC. Triangle BDC. In these two triangles, you have to prove these two triangles are congruent so that I equal to R. So three things you have to prove equal. Here this AC is equal to BD. Both cover same distance. The AC is equal to BD. Again this is wavefront and this one is ray. This is 90 degree. Again this one is wavefront. This is ray. This is 90 degree. So angle A equal to angle D and this BC is common. In this way you prove that these two triangles are congruent and therefore angle I equal to angle R. Hope it's clear to all of you, right? So in this way you prove laws of reflection that angle of incidence is always equal to angle of reflection. Now second law, this incident wavefront, this reflected wavefront and this reflecting surface XY all lie in the same plane. So here I have written notes, laws of reflection, incident wavefront, reflected wavefront and reflected surface all lie in the same plane, and how you prove these two triangles congruent. So angle I equal to angle R, right? Next, refraction of plane waves using Huygens principle. Now also using Huygens principle you have to prove laws of refraction. Again there are two laws of refraction. First one is what? Snell's law. Sin I by sin R is a constant quantity. Then how you prove this one also using Huygens principle? It means you have to prove using wavefront. Again you consider sources at infinity, parallel rays are coming. So this one is incident plane wavefront. Now here refraction takes place, so medium changes. In this medium suppose velocity is V1 and second medium velocity is V2. In first medium refractive index is N1, second medium refractive index is N2. Now when the disturbance from B point reaches to C after some time t, it covers V1 distance. At the same time disturbance from A according to Huygens principle reaches to this D point, covers distance V2t. V2 is less than V1. V2 is refractive velocity in denser medium, V1 is velocity in rare medium. Right now? So if you draw a common tangent over these wavelets, you get new wavefront, that is called secondary wavefront. Okay, and Using these two triangles, you have to prove sin I by sin r equal to constant. So from this triangle ABC, you find sin r, right? Again triangle ADC, again you prove sin r. Why this is I? This one is I, normal and incident ray, right? So this angle is 90 degree, incident wave front and ray. So this becomes 90 minus I, that's why this is I. Angle between this incident wave front and refracting surface is I. Again this one is R. So what is sin I from this triangle ABC? Yes, sin I is BC by AC. BC is what? BC is this one, V1T, and AC is this one. Okay. So just find sin I first. Sin I BC by AC. BC is V1T. So you get sin I equal to V1T by AC, equation number 1. In the same way, sin R. Sin R is what? Sin R in this triangle ADC. Sin R is AD by AC. AD is what? This distance V2T by AC. Okay. So V2T by AC. So in this way you get sin R equal to this one. When you divide these two, you get sin I by sin R equal to V1 or V2, which is a constant quantity for a given pair of medium. And hence in this way you prove Snell's law. This constant quantity is known as refractive index of medium 2 with respect to medium 1. And also, what is first law of refraction? The incident wavefront AB, refracted wavefront CD, and refracting surface XY all lie in the same plane. In this way, you have to prove laws of reflection and refraction using Huygens principle, right? Hope it's clear to all of you. After this, I'm going to discuss next topic, that is about interference. Okay. So before starting interference of light, you must know principle of superposition of waves. What is this? When two or more waves superimpose at a particular point in the medium, the resultant displacement of the particle is equal to vector sum of displacement due to individual waves. Suppose there are two waves, one is this one, another one is this one. These two waves superimpose at a particular point in the medium, like this one. These two waves superimpose. Let this y1 is displacement produced at this point due to first wave, and y2 is displacement produced due to second wave. So what is resultant displacement at this point? The resultant displacement is given by vector sum of displacement due to individual waves. Right? Now there are two types of overlapping or superposition. When crest of one wave superimpose on the crest of another wave, then what happens? Resultant amplitude increases, and you know intensity is directly proportional to square of the amplitude. If amplitude increases, intensity is maximum at this point. And this is called constructive overlap or constructive interference. Why interference? Because the effect produced by superposition of two or more waves is called interference. It means these waves are in phase. I will tell you what is phase. When the waves are in phase, then constructive overlapping takes place. But when the waves are out of phase, it means crest of one wave superimpose on the trough of another wave, then the resultant displacement is what? 0. Resultant amplitude is 0, resultant intensity is 0. And this type of overlapping is called destructive overlap or destructive interference. So hope it's clear to all of you. When the waves superimpose in phase, then constructive interference. When the waves are out of phase, then at that case intensity is minimum and it is called destructive interference. Now what is this phase? Okay, equation of wave you know, y equal to sine omega t. This argument of this sine or cosine, this omega t, this is called phase. And suppose there are two wave equation, one is y equal to a sine omega t, another one is y2 equal to a2 sine omega t plus 5. What is difference between these two phases? This one is omega t, this one is omega t plus 5. So difference between two phases are called phase difference phi. And what is path difference? Difference in path length of two waves meeting at a place is referred to as path difference, and the relation between path difference and phase difference is this one. Phase difference is equal to 2 pi by lambda into path difference. Phase difference phi is equal to 2 pi by lambda into path difference, or path difference is lambda by 2 pi into phase difference. You must remember these points. Now next I am going to discuss in detail what is interference of light. When two lights superimpose, then at the point of superposition, intensity of light is maximum at some points, right? And in some points, intensity is minimum, right? So this redistribution of energy due to superposition of two waves which are traveling in the same medium and the same direction is called interference of light, right? There are two types of interference already discussed: constructive interference and destructive interference. Constructive interference takes place when crest of one wave falls on the crest of another wave, amplitude is maximum and waves are in phase. This type of interference are called constructive interference. Destructive interference, the crest of one wave falls on the trough of another wave so that amplitude is minimum and displacement of these waves are not the same, that is they are out of phase. So these are two types of interference of light. Now to produce interference, coherent source is required. What is this coherent source? Coherent sources are those sources if they emit light waves of same wavelength and have a constant phase difference wave between them. Constant phase difference means the two waves, the phase difference must always be same. It may be 0, 30 degree, 40 degree, but this is always constant. Constant phase difference between them. Then these sources are called coherent sources. And to produce interference pattern, coherent source is required. Incoherent source, two sources of light which do not emit light waves with a constant phase difference are called incoherent source. So in nature, coherent source is not available. You have to produce this coherent source because two independent monochromatic source are not coherent source. Why? Because they emit waves of same wavelength but they are out of phase. Their phase difference is not constant. This is because atoms cannot emit light waves in phase and these sources are said to be incoherent. That's why two independent sources never be a coherent sources, right? Now, interference due to two waves. When two waves superimpose, what happens? At some point there is maximum intensity, at some point there is minimum intensity. So what is the formula for that intensity? To calculate that one, suppose let the two waves, first one is y1 equal to a1 sin omega t, another wave is y2 equal to a2 sin omega t plus 5, where this small a1 and small a2 are individual amplitude. Phi is phase difference and this I1, I2 let be individual of intensities of individual waves. So after applying superposition principle, you get resultant amplitude A has under root a1 square plus a2 square plus 2a1 a2 cos phi, where a1 and a2 are amplitude of the resultant waves and phi is constant phase difference between them. You know intensity is directly proportional to a square of amplitude. So resultant intensity becomes I equal to I1 plus I2 plus 2 under root I1 I2 cos phi. Here from this equation, it is clear that the total intensity is not just sum of intensity due to individual waves, but there is some extra term. This extra term is called interference term. This cos phi is called interference term, and due to this interference term, intensity may be maximum or minimum at the point of superposition. These two are waves. These two waves meet at this point on the screen. Suppose at this point these two waves meet. So at this point intensity may be maximum or minimum depending upon this interference term. So what is the condition for maximum intensity and what is the condition for minimum intensity? You know the maximum value of cos phi is what? 1, and 1 is only when phi is equal to 0 or 2 pi. So phase difference must be integral multiple of pi, right now. In that case maximum intensity is there, and you know path difference is what? After calculating this one, path difference is 2 pi by lambda into phase difference. You get delta equal to n lambda or 2n lambda by 2. It means even multiple of lambda by 2. When the path difference between these two waves are even multiple of lambda by 2, in that condition is the condition of maximum intensity. What is the condition for minimum intensity? Minimum intensity when cos phi is minus 1 and cos phi minus 1 when phi is 180 degree or 2n plus 1 pi n equal to 1, 2, 3. It means path difference becomes what? 2n plus 1 lambda by 2 where n is plus minus 1, 2, 3. It means path difference must be an odd multiple of lambda by 2, then that is the condition of minimum intensity. So maximum intensity when path difference is even multiple of lambda by 2, you must remember this point, and minimum intensity when path difference is an odd multiple of lambda by 2. And what is the value of maximum intensity? I maximum. This cos phi is 1, it means I1 plus I2 plus under root 2, I1 plus under root 2, I1 I2, and it becomes I1 plus I2 whole square. This is maximum intensity. What is the value of minimum intensity? I minimum. I1, this cos phi is minus 1, it means I1 minus I2 whole square. This is the value of minimum intensity. So in this way, you must remember these 2 points. When condition for maximum intensity, path difference is even multiple of lambda by 2, and condition for minimum intensity, path difference is odd multiple of lambda by 2. After this, next I am going to discuss Young's double slit experiment. You know, Huygens was the scientist who proposed wave theory of light, but this Young explained experimentally in this Young's double slit experiment. In this experiment, we need two coherent sources. And how coherent source is produced? Because two independent sources never be coherent source. So suppose there is one point source, and by any method we have to produce two coherent source S1 and S2 from this same source. Now this S1 and S2 are two coherent source. These two sources superimpose at a point P on the screen by superposition principle. Now here at point P, alternate bright and dark bands are formed on the screen, and these are called fringes. Suppose that D is the distance between the two slits, a small d, and capital D is the distance between source and slit. Now, what is the path difference between these two sources, S1 and S2? S1P first source and S2P path difference by the second source. So what is the path difference? Path difference is this S2P is greater than S1P. So path difference is delta equal to S2P minus S1P. And with the help of this geometry, you have to calculate this path difference. And this path difference is given by delta equal to X small d by capital D. What is this small d? Small d is distance between the two sources, capital D is distance sources. This small x is the position of point P from this central maxima. Why it is called central maxima, center of the screen? Because at the center of the screen always maximum intensity is there, because path difference from the two sources here S1O and S2O are 0, and if path difference is 0, it means this is the condition of maximum intensity, delta equal to 2n lambda by 2. If path difference is 0, it means this is the condition of maximum intensity. So central fringe will always be bright. Now after this central fringe has bright fringe means maximum intensity. Now at the point P, intensity may be maximum or minimum. So after central maxima position of maxima or constructive interference, when at point P constructive interference takes place or maximum intensity. So you have to calculate this position x from this figure. This is the what is the value of x from the center of the screen when maxima is formed. What is the distance x when minima is at point P. So you know maximum intensity, path difference is what? Path difference must be n lambda, or you can say even multiple of lambda by 2, and path difference with these two sources of what? X small d by capital D. When you calculate, you get x equal to n lambda capital D by small d. This is the position of maximum intensity at point P, and maximum intensity is called constructive interference, or you can say bright fringe. In the same way, what is the position of minima or destructive interference or dark fringe? Minima is obtained when delta is equal to 2n plus 1 lambda by 2. Odd multiple of lambda by 2 where n equal to 1 to 3, because at n equal to 0, central maxima is there. So path difference is x d by d. After calculating this one, you get x equal to 2n plus 1 lambda capital D by this 2d. This is the position of minimum intensity. So you must remember these two formulas. It is very, very important in Young's double slit experiment. Position of maximum intensity is x equal to n lambda capital D by small d, and position for minimum intensity is 2n plus 1 lambda capital D by 2d. And at the center, maximum intensity is there, like this one. At the center, maximum intensity. Then this is the position of first minima. Then again next maxima. Then again. So on both sides of the screen, like this one, pattern is formed. This is interference pattern, right? Now after this, next is fringe width. What is this fringe width? Distance between two consecutive bright or dark fringe is called fringe width. So you know position of bright fringe is what? N lambda capital D by small d. So distance between two consecutive, suppose this is like this one. Okay, this is central maxima. So distance between these two consecutive bright or dark fringe. These are two, like this one. These are two consecutive dark fringe. These are two consecutive bright fringe. Distance between these two consecutive bright or dark fringe are called fringe width. So how you calculate? You know, suppose distance of nth bright fringe from the center is xn is n lambda capital D by small d, and distance of n minus 1th bright fringe from the center is, suppose first, second or second, third. So nth and minus 1th bright fringe. Distance between these two bright fringe, you can calculate fringe width. It is denoted by beta. And when you calculate this one, you get lambda capital D by small d. This is fringe width for bright fringe. When you calculate for dark fringe, again it becomes beta equal to lambda capital D by small d. It means fringe width for both and bright or dark fringe are same. It means all bright and dark fringe are separated by equal distance, right? After this, angular width of the fringes. What is this angular width? Angular width of the fringes double slit is given by theta equal to lambda by small d. You must remember this formula. And you know beta is what? Lambda capital, this is beta. Beta is lambda capital D by small d. So this lambda by small d is theta. So from here you get theta equal to beta by capital D. This is the formula for angular width of the fringes. So you must remember this formula also, and this is independent on n. Here there is no n. So angular fringe width is same throughout, right? Now, you note this point. If the apparatus of Young's double slit experiment is immersed in a liquid whose refractive index is mu, then what happens? Fringe width increases or decreases? When the apparatus is immersed in a refractive index whose refractive index is mu, then its fringe width decreases. New fringe width becomes fringe width by mu. Fringe width decreases, right? Now, what happens when in place of monochromatic light, white light is used in interference? What happened in Young's double slit experiment? Then colored fringes are obtained on the screen with red fringes larger in size than violet fringes. So these are about interference, and this is intensity distribution curve for interference. Central maxima is there, then minima, then maxima, then minima, then maxima, then minima. You know, position of maxima is what? X equal to n lambda capital D by small d. X equal to n lambda capital D by small d. This is position of maxima or bright fringe. And position of minima is what? X equal to 2n plus 1 lambda capital D by 2d. This is the position of minima or dark fringe. Now at the center, distance from center fringe, x is 0, this is x. When x is 0, central fringe is there. When you put n equal to 1, it becomes lambda capital D by small d. So lambda capital D by small d, again at this point, first fringe is there, first bright fringe is there. And when you put n equal to here 1, it becomes, when n is 0, it becomes what? Lambda capital D by 2d. This is first minima. And this one is first maxima. Lambda capital D by small d. And between this central maxima and first maxima, first minima is there. Again, second minima, when you put n equal to 1, 3 lambda capital D by small d. Third minima 5 capital D by lambda capital D by 2d. So in this way, first, second, third maxima and minima are obtained on both sides of the screen. All are separated equally. All bright fringes are of same. All dark fringes are of same intensity, right? And distance between any two bright or dark fringe is same. So this is intensity distribution curve for interference pattern. After this, one important term is there. What do you mean by sustained interference? Sustained interference is the interference pattern in the position in which the position of maximum and minimum intensity remain fixed with time. It means maxima is found, minima is found. There is no change in intensity. Intensity remains fixed with time, and this is called sustained or permanent interference. And what are different conditions to get sustained interference? Two sources of light must be coherent. The frequencies of every two waves should be equal. The light must be monochromatic. The amplitude of interfering waves must be nearly equal. The two sources must be narrow. These are different conditions for sustained interference, right? After this, last topic of this chapter is diffraction of light. What is diffraction of light? You know, light always travels in a straight line. But when anything comes in the path of light, what happens? It changes their path. It depends upon the size of the obstacle or aperture which comes in the path of light. And this phenomenon of bending of light around the corners of an obstacle or aperture with a size equal to the wavelength of light used is called diffraction of light. This diffraction of light only takes place when the size of this obstacle is equal to the wavelength of light used. Otherwise, diffraction phenomena does not take place. Okay. Now, there are two types of diffraction. One is Fresnel diffraction and another is Fraunhofer diffraction. We have to study only Fraunhofer diffraction in this chapter. But what is the difference between these two? When both source and screen are at finite distance from this Fresnel diffracting device, or you can say aperture, then this is called Fresnel diffraction, right? This is the slit, this one is source, this one is screen. Both are at finite distance from the obstacle or aperture. This is called Fresnel diffraction. As both are at finite distance, so no lens is required in case of Fresnel diffraction, and wavefront is either spherical or cylindrical, right? What is this Fraunhofer diffraction? When both source and screen are at infinite distance from the diffracting device. This is slit. Both source and screen are at infinite distance. And infinite distance means here lens is required. And what type of wavefront? Instant wavefront is? Yes, instant wavefront is plane wavefront, right? So this is difference between Fraunhofer diffraction. Now I am going to discuss the most important topic of this chapter, that is diffraction due to single slit. Okay, it is very easy. It is just here in condition of maxima, minima is reverse of that of interference pattern. Suppose this parallel wavefront is incident on this slit AB. Let size of the slit or slit width is A. A is the slit width, right? Now rays are coming parallel, but due to this slit, it bends to some angle theta. This, according to Huygens principle, each point on this slit acts as a source of secondary wavelets which are in same phase. So these wavelets spread out in all directions and forms diffraction pattern on the screen. These rays are focused at one point on the screen with the help of this convex lens. Those which are not diffracted, which goes straight, meet at the center of the screen, and those which are diffracted through some angle theta meet at this point, suppose P on the screen. Now, here in this case, at the center of the screen, maximum intensity is there. Why? Because the rays emitted from this point A and B both are in same phase and path difference is 0. So, at the center of the screen, always maximum intensity, and this is called central maxima, right? So, here it is written that at the center of the screen, the rays emitted from A and B both are in phase and get converged at point P. Here, all rays are meeting at P in same phase, produce a central maxima. Now, after maxima, minima is there, then secondary maxima is there. Why it is secondary maxima? Because central maxima is maximum intensity, other maxima has decreased in intensity, so they are called secondary maxima. So, after central maxima, then suppose this is central maxima. Now, after this, first minima is there, then again maxima, then again minima. So what is the position of minima? Here position of minima, path difference between the two rays emitted from A and B, suppose A sin theta equal to n lambda. A is slit width, right? And this is the position of n, path difference n lambda is maxima in case of interference pattern, but in case of diffraction pattern, this is the position of minima. A sin theta equal to n lambda, where lambda is wavelength of light. Is when you put n equal to n, you get first minima, n equal to 10 to b, you get second minima, and so on. An angle of diffraction at which minima is produced is given by theta equal to, when theta is very very small, sin theta tends to theta, then theta equal to n lambda by a. Now after this, position of secondary maxima. It is the position which is minima in case of interference pattern. A sin theta equal to n plus 1 by 2 lambda. You can say A sin theta equal to 2n plus 1 lambda by 2. This is the position of secondary maxima. When you put n equal to 1, you get first secondary maxima. First secondary maxima is formed at lambda by 2. When you put n equal to 2, you get second secondary maxima. In this way, maxima, minima are formed. So what type of diffraction pattern is formed here? At the center of the screen, maximum intensity is there at this point O. Then first minima is formed at theta is n lambda by a. This is not d, sorry, it is a. All these are a. So first minima, when you put n equal to 1, you get theta equal to lambda by a. At the lambda by a, first minima is formed. When you put n equal to 2, it means 2 lambda by a. Second minima is formed, 3 lambda by a. Third minima is formed, right? And what is the condition for maxima? Condition for maxima is what? Okay, theta equal to 2n plus 1 lambda by 2. This is the condition for maxima. So you put n equal to 1, 2, 3, you get first secondary maxima, second secondary maxima, third secondary maxima. First secondary maxima has less intensity than the central maxima. Then next secondary maxima, this one is, these are all are secondary maxima of decreasing intensity, right? Here this one is first secondary maxima, this one is second secondary maxima, third secondary maxima, and all have decreasing intensity as compared to central maxima. So this is diffraction pattern due to a single slit intensity distribution pattern. So one line is written here. In case of single slit diffraction pattern, it shows bright central maxima followed by secondary maxima on either side of it, with there being points of zero intensity, means minima in between them. And width of central maxima is directly proportional to wavelength of light is inversely proportional to the width of the slit. So only these things are enough in case of diffraction due to a single slit. Now at last, one more thing. What is the comparison between interference and diffraction? Okay. So you have to compare or difference between interference and diffraction pattern. What is difference? This is the intensity distribution pattern for interference. All maxima are of same intensity. This side intensity, this side is phase difference phi. This one is interference. But here maxima are of decreasing intensity. These are intensity distribution pattern for interference and diffraction, and these are some differences. What are these? First one is interference is due to superposition of two waves coming from two different sources, but diffraction is due to superposition of secondary waves originating from different parts of the same source, same wavefront. Here width of interference bands are of equal. Here width of different bands is not the same. Different bands have different width. Intensity of all maxima is same here, but here there is decreasing intensity. Intensity of central maxima is maximum and goes on decreasing rapidly with increase in order of maxima. So these are some differences between interference and diffraction. And this is with this I'm going to end my class. Hope you like this quick review series of class 12th physics of term 2 syllabus. After this, which chapter you want for quick revision? Please write in the comment box. Okay students, up to then, keep revising and stay tuned with this channel. Thank you.